Good afternoon, everyone. Thank you for attending. And those of you who are watching the video, thank you for watching the video. As I mentioned, today I'm going to what's going on? Okay. Some funny stuff is happening. Okay, so yeah, last term students raised an issue that they were not comfortable with condition variables. That's why I thought that this term I run an example, a more detailed example using condition variables. Hopefully that helps you get up to speed with condition variables. So here it comes. So today we're going to talk about ReaderWriter Lock. So you should know the concept from 252, ECE 252. The problem that we want to address is that like you have a database that has multiple writers and multiple readers. Now, this data is shared between readers and writers, and you want to protect it from race conditions. In particular, you want to have this. Basically, if there is a writer, if thread 1 is writer, you don't want any other writer to have access to the data. Do we have the slides as a PDF format? I have just before the tutorial, I updated the website. So just refresh the website in the schedule for today's slot. You should find the PDF and PPTX formats. Okay, so if you have a writer, you don't want anybody else to be modifying the data or reading the data. So if you have any writer in accessing the data, no other writers, no other readers. If, however, you have a reader, then you definitely don't want anybody to write, but you're okay if other readers also access the data. So this is what we want as a requirement for our lock. So we want to implement a lock that that we can use it this way. So here's the implementation. Here's what we will have. So we're implementing this reader or read-write lock. I would have, yeah. Anyways, so this has one monitor. This monitor has a lock and 2 condition variables. So I actually apologize for having this lock here. Consider it as a mutex. I got the slides from SE 350. There I just was talking about locks, not mutexes. I just changed all my locks to mutex because I knew that you guys studied mutexes instead of locks in 252, and I didn't want it to be confusing. I forgot to change it here. But anyways, this is just mutex. Yeah, I'm calling it lock. So we have one mutex or one lock, 2 condition variables, okay to read and okay to write. And then I have 4 variables. This is active writer, active reader, waiting writer, and waiting readers. And all of them are initiated to 0. Now, my lock has 4 public functions: acquire reader lock, release the reader lock, acquire writer lock, and release writer lock. So if I were to just modify this as we go, this would be a mutex. mutex of mutex. I will probably modify the entire thing after today's lecture, so you probably will see the changes. So this would be lock the reader lock, and then unlock the reader unlock, and this would be lock as a writer and unlock as a writer. And probably we would want to call this reader writer mutex. Something along those lines. It's just fine. So I just did this, but to get your minds aligned with what I'm gonna see. But I hope it makes sense. Okay. Now let's get to implementing this. So the pattern that we want to have with this mutex or with this lock. Maybe I shouldn't actually. Never mind. I apologize for this. I'm not gonna call it mutex because mutex has its own meaning. So let's keep it as a lock. And keep these as acquire and release. So the only thing that I changed here is this mutex, and probably I would want to call it ReaderWriter Lock. That's it. So we're going to call them acquire and release, so the only thing that I changed here is the mutex. Hopefully that makes sense. Okay. Now here's the pattern of using this. So if you are a reader thread, you want to lock and then acquire as a reader, and then you read the shared data, and then you unlock. So basically lock release. And if you are a writer, you want to lock it as acquire. You want to acquire the lock as a writer, then you would access the shared data, and then you unlock. So this is basically what we want to implement. And we want our lock to be used this way. Okay, now let's get to implementing the reader lock. As always, so this is the position that I have to now do this change, mutex dot lock. And here I'm gonna do the mutex dot unlock mutex. I probably shouldn't do this. I should assume that you know what I'm talking about. So this probably will be the last one I'm changing. The rest of them I will go with the lock, and then eventually I'll clean it up and release it again on the website. Okay. Okay, as always, at the beginning of my function, I'm going to acquire the lock or lock the mutex. And then I'm going to do a test. So while active writers and waiting writers are greater than 0, I'm going to become a waiting writer. So waiting writer ++, and then I will wait on my condition variable. So OK to read, it's not OK to read, so I'm going to wait on it. And I'll send the reference to the mutex, to this wait. When I wake up here, let's say after I get a signal, then I'm going to reduce the waiting writers by 1, because now I'm not anymore a waiting writer. But then I'm going to go back to this while. If you remember, this is a Mesa implementation, so I'm going to go back to this while, check it again. And if things were OK, then I will get out of this. But if things are not OK and I cannot read, then I'll go to sleep again. So if I get out of this while, I become an active reader. So active reader ++ and unlock the mutex. So why release the mutex here? Why unlock the mutex here? The reason is this mutex is not the mutex that we're using to protect our critical section to access the shared data inside our database. This mutex is an internal mutex for this class ReaderWriter Lock. And this is where I'm actually changing the state of my ReaderWriter Lock. And that's why I'm locking it and unlocking it here. Again, this mutex is only used to protect the internal state of this lock. It's not the mutex that I'm going to use to protect my critical section when it comes to my database that I'm using this lock. Basically, this lock is going to be used to protect that critical section, not this mutex. So this mutex is just for internal use. That's why I'm unlocking it here. So that's the answer. So this lock is acquired to change the internal state of ReaderWriter Lock. Now let's look at the release reader lock. Again, at the beginning of my function, I acquired I lock the mutex. Now that I'm releasing the reader lock, so I'm no longer an active reader. So active reader --. Now I want to see if anybody is waiting for this. Who could be waiting? Well, there might be writers waiting, and the only time that I have to signal them is if there is no other active reader. So if I'm the last active reader, I can signal a waiting writer. So that's what I'm going to do. I will check if there is no other active reader, but there are waiting writers, then I will signal them. So I will tell one of them to go ahead and write or wake them up. And here I unlock the mutex. Again, unlock the mutex and we'll be done. Okay, so I got a question. So by the restricting access with the ReaderWriter Lock, aren't you also protecting the data? So yeah, so the ReaderWriter Lock is going to be used to protect the shared data inside the database. This mutex is going to be used to protect the shared data of the lock. So there are two sets of data that we want to protect. One is the internal variables of the ReaderWriter Lock, and one is the data in our database, which we will use this ReaderWriter Lock to protect. So you have to distinguish between the two. That was the point I was raising. Okay, now let's this time inside release RL, why aren't you also checking waiting readers? So hopefully there are no waiting readers, right, at this point, because it's okay for to have as many readers as you want to have. So if you have one reader, other readers that come, and if there are no other waiting writers, then readers can go in. But if there exists a waiting writer, then new readers will wait, as you can see here. So let's say this is a scenario. Reader 1 comes, acquires the lock, gets into the database, so has reader access. Now thread 2 comes, it's a writer, so it checks there is an active Yeah, you haven't seen the acquire writer code, but what it does, it checks and it sees that there is an active reader, so it will wait, becomes an waiting writer. Now let's say thread 3 is another reader. This thread 3, when it comes, it checks here. Because there is a waiting writer, it doesn't get in. It waits. Although it would have been okay for it to go inside, but because there is a waiting writer, it sits out. So as you will see, I will actually analyze the code later. As you can see, this code gives priority to writers, and it could starve readers. We'll discuss the properties of this code later. So just to confirm, you mean that you're trying to protect active reader, waiting writer variables with the mutex.lock, right? Yes, exactly. That's exactly what I'm doing. So if I go back to this slide here, so this is my class that I'm implementing right now. So this is my class, and these are the internals of this lock. And then every thread that uses this lock might change these. So to protect it from race conditions, I use this mutex to protect the internal state of the lock. Now then, I will use this lock to protect my database. So this is my database. Let's say I have a database. I will use this lock eventually to protect the data in my database. I use this mutex to protect the internal state of my lock. Now let's see the writer, acquire and release functions. So acquire writer, you, as always, acquire the lock or lock the mutex. Now you check if there are any active writers or active readers, you have to wait. So here you become a waiting writer, and then you wait on your condition variable. And when you wake up from this wait, as I mentioned during the lecture, the first thing you do, you acquire this lock. If this lock is acquired by someone else, you will go to sleep here again inside this wait. And then when the lock is unlocked, you lock it, you get out of wait, but then you have to check again to see if you can go. And if you cannot go, then you go again to sleep here on these condition variables. So you could go to sleep. So this wait put you to sleep on this condition variable. When you wake up from this wait, you wake up inside this, and then you have to acquire this lock. And if this lock is acquired by someone else, you will go to sleep again on this lock. And then later on, when this lock is freed or released, at some point you will wake up, you get out of wait, and then you check again. So that's the whole idea about this. Once you're out of this while, you become an active writer, and then you release the lock. This is the release the lock. Very similar. Here, I think we do one extra thing. So in order for us to signal if a writer is getting out, then it checks first other writers, see if there are any waiting writers. If there are any of them, it signals one of them. If there are none, then it could broadcast to every waiting reader. So if there are no waiting writers, I can broadcast all the readers to go ahead and read, because all of them can go in this model. And then I release the lock. I got a question. So it seems like we're giving priority to writers. Yes. Why don't we make a data structure that stores information about readers and writers, sorted with writers having higher priority and pop from that? I actually have some slides for you. So just wait on this. Yeah, we're gonna go there, sort of. So just if you don't get an answer on that, ping me again. Great. Now let's run this code with this following sequence. Let's say we have a reader 1, reader 2, writer 1, and then reader 3. Let's see what happens. This is the code. So reader 1 comes in, acquires the lock. So I have the internal state here for you to see, and then the code I'm running through the code. Okay, so it checks active writer plus waiting writer is 0. So we just jump. We become active writer. So active writer becomes 1, as you can see here. And then we get into the data. Let's say at this point, reader 2 comes. So reader 2 comes, acquires the lock. This lock is unlocked. This is the mutex, basically. The mutex is unlocked because the reader 1 released it here. So it can acquire it. It will check the internal state of the lock. Active writer plus waiting writer is indeed 0, so it can go. It becomes an active reader. It can release it. So now I have 2 active readers. Both of them are reading the data. Let's say at this point, let's say the reading takes some time, yeah. So let's say that writer comes while the readers are reading. So now writer 1 comes. It acquires the lock. Lock is free. This is basically the mutex. Now it checks if there are any active reader. Well, there are. So there are 2 active readers. So this while goes inside. So this thread becomes a waiting writer. So waiting writer plus plus, as you can see here, waiting writer becomes 1, and it goes to sleep. So here, writer 1 cannot start because there are readers. So it releases the lock. Here, it releases the mutex basically and goes to sleep. Now at this point, we have 1 waiting writer and 2 active readers. Let's say at this point, reader 3 comes. So reader 3 can actually acquire this lock because writer 1, when it went to sleep, it released the mutex. So we can get that mutex. We ping the internal state of the lock. Actually, there is a waiting writer. Waiting writer is 1, so we will wait. So at this point, we become a waiting reader. So waiting reader now becomes 1, and we go to sleep. So now R1 and R2 are still reading. W1 and R3 are waiting. Let's say R2 is done. So it wants to get out. So it acquires the lock. It can lock the mutex. Now active readers minus minus. It checks because there is another active reader. So active reader is actually 1. It's not 0. So it doesn't do anything. It releases the lock. It gets out. Now let's say at this point R1 is done. So it wants to release the ReaderWriter lock. So it acquires the lock or the mutex. It decreases active readers by 1. So now active readers become 0. Now, because active reader is 0, and there is actually 1 waiting writer, this is the waiting writer. So it can actually signal that waiting writer. So at this point, it signals. What does it do? So all this does, and nothing more, it just changes the state of W1 from waiting to ready, and that's it. So it puts the W1 thread onto the ready queue, so that the scheduler at some point can schedule this thread. and then it just releases the mutex or unlocks the mutex and gets out. Now, let's say the scheduler picks up W1 because W1 is ready. It can execute. Where does it wake up? It wakes up inside this wait function. The first thing it has to do before exiting this wait function is to acquire this lock or this mutex. At this point, there are no other threads in the system, so the mutex or the lock is free. So this should be easy to acquire the lock. Once the lock is acquired, it gets out of wait. So now we get out of the wait. We are no longer waiting. So waiting writer minus minus, but we have to check again. So we go. We have to go back. I've jumped from it because this condition is not does not hold, because there is no active writer or active reader. So we get out of this. So we are here. Active writer becomes ++, and we get into the code. Once the W1 is done, here it checks. It sees that there is actually one reader waiting. So it broadcasts. It wakes up the reader. So now reader 3 wakes up here. It does all the things that I said. It becomes active reader. It goes and reads, and then it releases. So that's basically it. Now let's analyze this code and see what it actually does. How does it prioritize stuff? And let's make some changes, see what happens. So this is one change. I want you to think about what happens with this change. Let's say I remove this line, this if, and I just signal without this if, right? What happens? Does this work? Let's say I don't check to see if there are active readers or waiting writers, and I just signal. Would this work? Am I changing the semantic of my lock? Would things go wrong? I'm going to just wait a little bit and then answer the question so that everybody has some time to think about it. So basically, this is releasing the reader lock. And I'm saying, instead of checking, just signal. Just signal. The answer is, actually, it works. So it's not going to change the semantics or the correctness of your implementation. The only thing that is going to change is efficiency of your code. It's going to make your code less efficient. Why? What happens is, if you eliminate this if and just signal here, let's say that you do have a waiting writer, but let's say that you also have some active readers. What would happen? So this waiting writer will wake up. So its state becomes ready because it gets a signal. At some point, the scheduler will pick that writer. So the writer, well, where does it wake up? It wakes up here. Let's say it can acquire the lock. It comes out of this, but then it will check and it sees that, oh, there are active writers here. So it goes to sleep again. So basically what happens is we just wake up someone that shouldn't have been woken up, but still doesn't change the correctness of our code. It's just inefficient because this writer will wake up and then goes back to sleep again. It shouldn't have been signaled. Now, let's do another thing. Instead of signaling, what if I broadcast to all writers? Would this still work? Am I changing the correctness of my code if instead of signaling, I broadcast? So the answer is no. Still, it would work. So I'm not going to change the semantic or correctness of my implementation. The only thing that will happen is that my implementation again becomes inefficient. Why? Because I'm going to wake a whole bunch of waiting writers. So all of them will wake up at some point, and they're all going to just go through this. And probably only one, I mean, obviously, only one of them can go, right? So the first one who gets to run, the first writer that could get to check this condition and get over this while will change active writer to to 1, and then the rest of them, when they wake up, they will have to go back to sleep. So I basically created a load that was not needed by waking every single writer up because only one of them can go. So what's the point of broadcasting? I can only wake up one and be done with it. What if I, instead of having two different condition variables, OK to read and OK to write, what if I only have one? So OK to continue condition variable, let's say. So I use this OK to continue everywhere instead of having separate condition variables per type. Would this work? Again, giving you some time to think about this. So this wouldn't work, unfortunately. Let's see why. So this implementation wouldn't work. The reason is you could signal a wrong thread, and then that signal could get wasted. And if there are no other signals to come, then your system will get stuck. Let's see how. Let's consider the example we had. Reader 1 and reader 2 were inside the critical section, so they were reading. Then writer 1 came, it went to sleep. So now let's say it's writer 1 is is waiting on this OK to continue. And then reader 3 came, and it also got to wait on this OK to continue. So now I have writer 1 and reader 3 waiting on this OK to continue condition variable. Now, let's say R2 is done and it wants to go, so nothing happens. Then R1 is done. So when R1 is done, it checks and it sees that there are no other active readers. It also checks and figures out that there is actually one waiting writer. Now, what it does, it signals this OK to continue. OK, at this point, the signal will wake someone up. We don't have any guarantee that the writer is going to be the thread that would wake up. So this signal could potentially go to the reader. So reader 3 could get this signal. What happens to that? So the reader 3 is going to wake up. It's going to look at this and sees that, oh, there is no active writer, but there is a waiting writer. So I shouldn't do anything. I should go to sleep. So reader 3, after waking up, it checks again and puts itself to sleep again. And what happens now? If those 4 threads were the only 4 threads that you had, now R3 and W1 will wait forever. Nobody's here to wake them up anymore. So the signal got wasted. We woke up a wrong thread, and that thread put itself back to sleep, and now there is nobody else to wake anybody up. And that signal is wasted and the system doesn't work. What if instead of signal we do broadcast, so that we wake everybody up? Instead of just waking up the reader, we broadcast. So this one actually will work. This implementation will work, but it's super inefficient. So you're basically waking up everyone, and then one of them only can get out. That makes it super inefficient. Okay. Now, here is a question. Can readers starve? We sort of answered the question, right? The answer is yes. In our implementation, writers have higher priority than readers. So if there is a waiting writer or an active writer here, the readers will put themselves to sleep. So you could imagine that, you have writers coming every 5 minutes, and each one of them is going to take 5 minutes. Then all the readers will be packed, will be put to sleep, because once one writer is done, another writer comes. And as long as you have a writer in the system, waiting or active, readers are going to put themselves to sleep. So they could potentially starve. So that's an easy answer. It could be fixed, right? You can change these and how you put them to sleep to change this. But with this implementation, readers will starve. Now here comes the interesting question. Can a writer, a particular writer, starve? I'm going to give you some time to think about this. So comparing readers and writers, readers could starve. That was an easy question and answer. Now here is the interesting question. Can a particular writer starve in this implementation? I'm going to give you some time to think about it, and then I'll continue. Okay, unfortunately, we don't have much time, so I have to finish this. Yes, a particular writer could indeed starve. Let's see how. Do I have a slides for this? So I can explain. How can that happen? Let's say at this point, there is a writer waiting, writer 1, like back to our example, reader 1, reader 2, writer 1, and then writer 3. Let's say at this point, after reader 1 is done and reader 2 is already done, reader 1 will signal writer 1. So after this line, writer 1 becomes ready. It's not going to run. It's just going to become ready. And then reader 1 terminates. Right after reader 1 terminates, writer 2 comes. So now writer 1 and writer 2 are ready. So writer 2 is a fresh writer, and writer 1 just woke up. What happens? Let's say the scheduler picks writer 2 instead of writer 1, which is possible. So writer 2 is picked up. It comes here. It checks. There is no active writer. There is no active reader. So it becomes active writer. and it gets into to write. Now, at some point, a context switch happens. We go to writer 1, and then writer 1 comes and checks here, gets up out of wait, goes back to this while, and it checks, oh my God, there is an active writer. Why did I wake up? That's why the Mesa requires you to do this while. So it goes back to sleep. It puts itself to sleep. And now you can imagine that this could happen again and again and again. So this writer could be signaled infinitely many times. But every time that it wakes up, you could get a new writer who would come and get into this critical section, and when again this the one who woke up gets to run, there is an active writer, so he has to go back to sleep. So in this case, writer 1 could starve forever. The scenario that I just described, it's possible. So a writer could starve. How do we fix that? So here is a change. Let's see if this change solves the problem. Let's say instead of just checking for active writer and active reader, what if we also check for waiting writer? So check also for waiting writers here. And if there are waiting writers, go to sleep. Does this solve the problem? So the answer is no. This is not going to solve the problem. Why? Because if there is a waiting writer other than the one who woke up, then no waiting writer can proceed, right? So let's say writer 1 and writer 2 are waiting, and writer 1 gets a signal. Then writer 1 wakes up here. It goes back to check this. Well, there is writer 2 waiting, so it goes back to sleep. So this is super unhelpful. No writer could now get out if there are other waiting writers in the system. Okay, so that didn't work. Take 2. What if we sort of order our writers based on how long they have been waiting? So with the condition variables, you don't get to implement FIFO. So condition variables, the queue is not FIFO queue. It has some logic, but it's not FIFO. So there is no guarantee on who is going to get the signal. There is a guarantee that you will get the signal if you wait for a certain number of signals. So there is that guarantee, but other than that, there is no guarantee on who's going to get the signal first. Plus, even if you get the signal, once you get the signal, as I described, there could be a newcomer and a fresh writer who could come and get that from you to go and become a writer, and you have to wait. So how can we order our writers? We can actually do something like what you do in banks, or I think I did it here when I was applying for driver's license. So you get a number. When you get into the system, you press a button, it gives you a number. So that's your number. Since I don't have time, I'm going to actually ask you to read this code and then see that it won't work. With the first try that I have here, just adding this number would not solve the problem. It would still happen that you could wake up a wrong waiting thread and your signal could get wasted. So because I don't have time, I'm not going to spend time on this. So here comes the take 3 that will solve the problem. And take 3, instead of just relying on numbers. So we still give people numbers when they come to the system. So every time a writer comes, it gets a number. So this becomes their number. But then we also create a new condition variable for every writer. So instead of having only one condition variable and making everybody to wait on that particular condition variable, we create new condition variables every time somebody comes to the system. So everyone gets their own condition variable with this line, right? And then we could have a FIFO queue, and then we can queue these condition variables inside our FIFO. Now this is safe because we have this mutex locked. So this queue becomes a state again of our lock. So we can actually make sure that when we change the state of this queue, it's race free. So this way, I'm creating one condition variable for each writer, and I put them inside this queue. This is my own queue that I added to the lock. And when I want to wake somebody up here in release the writer lock or release the reader lock, I only signal the head of the queue. So I pick the appropriate condition variable, I dequeue it, and then I signal that particular condition variable. Because every writer has its own condition variable, this signal only goes to one person, and that person is the right person to get that signal, because I have a FIFO of these condition variables. So this way I can actually implement a starve-free reader-writer lock for writers. This doesn't solve the reader's starvation, but at least this implementation makes sure that there are no writers who get starved. So I'm glad I got a chance to finish this. I went 3 minutes over time, but thankfully I finished it. So thank you for everybody who attended. And hopefully this was a good practice for you guys to see condition variables in action. Sorry for the lock mutex stuff. I will change the slide and upload it again on GitHub so that all the locks are turned to mutex, appropriate locks to mutexes. Thank you so much for those who are watching as well. I will, yeah, I think this will be available on Teams. I'm not gonna upload this on YouTube, so it will remain on Teams. So whoever watches it on Teams, thank you for watching, and take care, be safe. Talk to you on next Tuesday. Bye-bye.